Okay, thanks very much. Yeah, I will talk about standard extension algebras. So this is a problem which relates to highest weight categories, which we already saw also a little bit this morning. So its prototype is in Lie theory category O with Verma modules, such a highest weight category. You can also think geometrically in terms of categories of Purver sheaves, or if you are more algebraically minded, you can think of take a projective generator of one of these categories, take the endomorphism algebra. What you get is quasi-hereditary algebra in the sense of Ringe, and combinatorially you might want to talk about decomposition numbers or Jordan-Hölder multiplicities. In this case, you get custom-Lustig polynomials. So an easy example of such an highest weight category is, as I said, given by category O. I make it a bit smaller and look at SLN, take the principal block, this is O0, and then I take a parabolic version for this maximal parabolic, which is drawn here. And then we have also parabolic Verma modules. In this case, we have geometrically the category of Purver sheaves on Pn. Pn has a stratification. If you want to say this is each stratum is an affine space, and I drew here explicitly one of the strata by these stars. It's an affine space. If you want to have it the algebraic description, you can think of modules over this parser algebra of this zigzag algebra quiver, which I drew below. And I put an end loop at the vertex 0. So going from 0 to 1 back to 0 is 0. And we can draw explicitly the projectives, which I did here in terms of simples. And you see in gray the Verma or standard modules. So they have a filtration by them. Okay, so and the task is, given such a highest weight category, take this direct sum of the standard or Verma modules and describe the algebra of extensions. Okay. And so parabolic category O, I think this is an old theory. It's well understood. If I'm in this maximal parabolic case, in particular the one we saw above, then the combinatorics is understood by Lars Kruschitz and Berset. Braden gave a nice description in terms of Purver sheaves in explicit terms. In modern terms, you can think of cyclotomic KLR algebras or Hovanov algebras. And quite recently also one could give a description with quivers and relations. Also, this is not very helpful often because you have lots of vertices in this quiver. But in principle, one should say we understand this. Okay, but this talk is about this extension algebra. And so let me say what comes from abstract nonsense. So we know that when we have these Verma modules, they form an exceptional segment, which means when I want to compute x, they are directed. So there can only be x in the direction of the partial ordering, which is data of the highest weight category. And also they generate the derived category because the projective has a filtration by these guys. So in principle, we can understand the derived category by understanding this extension algebra. So this is positive news, but here are negative things. So when we look at HOMs, this is in general pretty difficult. So in this example I drew above, one can explicitly just compute the HOMs. Fine. But you see already in this small example, it's not like in normal category O, where Vermas always embed into each other. So it's not embedding, it's something more complicated. And in general, it's totally unknown. We don't know what embeddings or morphisms between Vermas are, parabolic Vermas. And there's a famous conjecture attributed to Geber and Joseph in the 1980s. It says that the dimension of this X algebra is given by a certain polynomial, which is a famous R polynomial, which comes up in Castell-Lustig theory, and this one should be a T, so it's a polynomial in T. But a few years later, there was a counterexample by Bow that this is not true. And then nobody knew what actually this dimension is supposed to be. And there's quite a few papers, so I just list here two of them. But in particular, Abe has several papers where he computed certain x or non-vanishing x in degree 5, in degree 1, etc. But in general, the dimension of this extension algebra is known even for the classical category O. So the other problem is that higher structure is needed. And one sees this, if I would have been careful, I would have written this equivalence of derived categories, not just as an equivalence of triangulated categories, but it's actually an equivalence of A infinity categories, which is explained in a paper of Keller very nicely. And what we could show in an older paper, that this algebra E is in general not formal. In general, we have higher multiplication. So in the above examples of Pn, or this maximal parabolic of this special type, it is still formal because it's too small. But if you go to the Grassmannian 2-4 case, it's not formal. And this was reconfirmed recently in terms of symplectic geometry using Fukaya categories by Mack and Smith. So that means I want to come back and say, actually, we don't understand category O. I thought we would, but we don't. And even for this maximal parabolic case, we know dimension formulas for this X algebra, but we don't know the algebra structure, and we are far away from understanding, in principle, the A infinity structure. Okay, but here's some progress, which I did with Jens Eberhardt. And the statement is that if I want to understand this X algebra of all these Vermas, I can say, okay, it's some Hom in a derived category. And then the statement is it's given by the cohomology of a space. So I translate it into geometry. And this is an isomorphism as graded spaces, but also an algebra isomorphism by putting a certain convolution algebra structure on the space. And what I want to emphasize as well is, coming from geometry, there is a second grading. So there's the X grading from homology, and there's a second grading coming geometrically from a mixed Hodge grading. And in the example we had upstairs, it's just given by this path algebra by putting the arrows in degree 1. So we have a doubly graded algebra, and this is an isomorphism of doubly graded algebras. So why is this useful for somebody who is interested in combinatorics? So I have then the Poincare polynomial of this algebra, which is a doubly graded polynomial in Q and T. I can specialize the Q and I can specialize the T. I get two different polynomials, and one calculates, in this case, the X dimension. The other one calculates counting of points over a finite field. And the fact that these two things are not the same for these varieties is explaining the failure of this Gabor-Joseph conjecture. So also it refines the formulas for the dimensions of Shelton. And so in general, one often has the situation that in mixed Hodge structures, these two polynomials agree. But here the situation is just not so nice. And so Gabor had in principle the correct intuition, but was slightly off. So let me just quickly give an idea where this geometric setup comes from. So we have a very general construction, which is far behind this category O. So we have a smooth projective variety. Above it was Pn. You can take Grassmannians or flag varieties. You have an action of C star, which is usually coming from one parameter subgroup in a torus. You take fixed points. So I drew upstairs these points by these crossings. In this case of the Grassmannians, it's coordinate subspaces, which are these fixed points. And then you can ask which points are attracted to these fixed points. So I drew here a picture. The big ball is the fixed point, and the others are attracting along one parameter subgroup to this. Or you can also take repelling. And so the theorem says this X algebra is given by taking cohomology with compact support of the intersection of an attracting with a repelling cell. So these things are for flag varieties, or Grassmannians are famous varieties. They are called open Richardson varieties, or I would maybe call them Kastan-Lustig-Deodat-Richardson varieties. And so one wants to understand them. And so in the case of Grassmannians, every such repelling and attracting cell has a concrete parameterization. It's an affine space. And in principle, we just intersect affine spaces. But as I think most of you know, linear algebra situation can be very difficult. And in this case, it's very difficult to actually find a parameterization of this intersection. But this is one of the pieces which we do. So, and then what are the results? The results at the moment are that in the maximal parabolic case, we have an explicit description of this algebra E with a basis and a multiplication. And one can see that it's glued together from the SL2 case, so a two-dimensional one Hom and one X. And one can see this combinatorially also in this formula indicated by yellow. And moreover, we have an explicit diagrammatical DG model. And what is in progress is that we understand the complete A infinity structure. So here at the bottom, I have a picture of the Grassmannian 2-4 case of the quiver with relations. So they are really pretty handable. But the A infinity structure is in general very hard to compute. But talking to symplectic geometers, we realize that it's really, really helpful to use Fukaya categories for that. And we have a model which is based on Fukaya categories, which gives a very beautiful answer, but we have to somehow write up the details. And I think I stop here. Thanks.